right, so we're doing some optimization problems. Now the math behind optimizing, you guys already have. It's like find the derivative set to 0, check some y values. Often what you guys will need help with and practice with is actually given a scenario, actually creating a model for what you're trying to maximize and minimize can sometimes be the most challenging thing. So I'm going to do 3 examples with you today, setting up and solving an optimization problem, and then 2 or 3 more tomorrow, and then you guys will do some independent practice and hopefully just get good at that. This first one is a question that I know when I teach the grade 9 math course, we actually solve this problem. So the scenario is that a lifeguard at a beach, some like flat section of beach, is setting up a swimming area. So they're going to be putting some ropes and some buoys and making a rectangular swimming area. But of course, they don't need any they don't need to just lie some rope down on the beach. That'd be kind of silly. They only need the lines and the buoys out in the water. So the idea is, if this lifeguard has 200 meters of rope, there's many different swimming areas they can make. What is the ideal swimming area? The biggest possible area they can make using that 200 meters of rope. So you could make a swimming area where the width is this width here is a lot longer than how far out in the water you go. Or you can go really far out in the water and have a small width. Or maybe you can make a square. Who knows what the biggest area is? We're going to find it. Now, in the grade 9 course, and you might have even done a problem like this, in the grade 9 course, what you would do is you would just, there's only so many different lengths and widths you can do. Your teacher might have given you, okay, if the length is 10, what's the width? Find the area. If the length is 20, what's the width? Find the area. And you might have systematically gone about it just by calculating some areas and then plotting those points. This question I like too, because we can actually solve it using grade 10 math, because it winds up being a quadratic function when we set it up. But we're going to use this one to get into the flow of how we use calculus to solve these problems. All right. So let's begin. So in general, when you guys are solving an optimization problem, you need some kind of equation to optimize, to find the max and min of. And here we're looking for the maximum enclosed area. And so we need an equation for this area. Well, you guys know the area of a rectangle, so that's no big deal. So that to start off, we need to get an equation that we're optimizing. So the equation here, area equals length times width. I'm just going to use capital L and lowercase w, just like my diagram. Now, right away, we have an issue with this one, because this is a equation with 2 variables, and you guys haven't learned multivariable calculus yet. So we have to take this equation with multiple variables and get it into an equation with 1 variable, so we can do all of our calculus stuff with that. And we do that by coming up with by using the constraint we're given. We're told that not any swimming area is possible. There is 200 meters of rope to create our swimming area. That means we can make with 200 meters, we need to make 2 of those lengths and 1 of those widths. Remember, we don't need a width along the beach. And whatever that length and width is, we'll have to add up to 200. And this allows us to get an expression for the width. The width of our swimming area will be the amount of rope minus 2 of those lengths, whatever those lengths are. So far, this is still something that you would have been able to do in your grade 10 math course. But now we can take our area function and actually create an area function just in terms of the width. And I'm just going to write it like this. It's the width times the length, and the length is 200. Oh, what am I doing? We worked so hard. We worked so hard to get the Control Z. I apologize if you work in pen. We worked so hard to get the width in terms of the length. I want an area function in terms of the length. That makes way more sense. The width is equal to 200 minus 2 times L. And now we have an area function in terms of 1 variable. I could have got L by itself too and got an area function in terms of the width. But so now grade 10, you could finish this problem because this is quadratic. So you could find the vertex and find the length that maximizes the area. And maybe you even did this question in grade 10. But let's get in the flow of how we would use calculus to solve this problem. So using the extreme value algorithm, we know that the max is what we're looking for. It will be at either some critical points or the endpoints. So just to find the derivative, I'm just going to expand this out and get it to something that's easier for me to find the derivative of just by distributing this out. And maybe I'll write the L squared term first. So there's my area function, just expanding things out. Yeah, let's just keep going. Let's apply our algorithm now that we have a function to optimize. Instead of completing the square like in grade 10, let's find the derivative and set it to 0. This one's a pretty simple derivative because it's quadratic, so minus 4L plus 200. And we are going to set that to 0. Why? Because that's how we find critical points, any local max, local mins. And this isn't really a crazy complicated equation to solve. You probably might have even just be able to see with mental math that the length that makes that derivative equal to 0 is 50. So before we just wrap up this problem and say, oh, it's 50 meters for the length, let's just talk about a few more things. So now let's actually start answering some questions for part A. So we're finding the maximum enclosed area if there's no restrictions on the dimension. So can you guys just go back and have a look at our area function? Or just think about the problem in general. So our area function is in terms of the length. Can you guys just think for a second, and maybe I'll do my attendance while you guys think on this. What's the domain of this area function? I just can't plug in any L that I want. There's a lowest possible L, and there's a highest possible L, given the constraints in this question. So while you guys think on that domain, I'm going to pause the recording. All right, what do you guys? So what's the lowest possible value for L we could have? 0. That's right. Now, that might make a silly, if you think about what happens if length is 0, then what that swimming area would look like was the lifeguard would just go lay out 200 meters of rope along the beach, and you'd have a lot of sad kids because they couldn't go swimming, right? So obviously that's kind of silly. What's the biggest value for L we could have? Like if you had to put some rope out in the water and bring it back, what's the farthest you could go? 100, right? So the domain of this area function, the length can't be less than 0, and the length can't be more than 100. 100 is really silly too, because then you're just got like, it looks like this. This is your swimming area. You just loop the rope back and forth. So would you guys agree? These endpoints are obviously not it. These are not going to give us the maximum area possible. So let's continue here. Let's just pretend that we didn't know that those two endpoints give us silly looking areas. Let's apply the extreme value algorithm. We know that the biggest swimming area possible will occur at the endpoints, so when length is 0, or at any critical points. We found 1 when the length is 50, or at the other endpoint when A equals 100. So can you guys, that's a 50. Sorry, my fine motor 60 didn't magically appear out of thin air where we have 50. I will fix that. Hopefully that's satisfactory 5 for you. Check the area for those 3 values. Our maximum swimming area will be at one of those for sure. Now, hopefully it doesn't take too much thought to see when you plug in L equals 0, you get an area of 0. Same thing happens when you plug in L is 100. You get a sad swimming area of 0 meters squared. When you plug in 50, we get 50 times 100. I think you get 5,000, right? Can you guys confirm or deny? You get 5,000. All right. So we have solved this problem. Let's wrap it up. Maybe I want to make sure I have space for part B. So I'll just maybe tuck in a concluding statement here and a little visual. The largest, let's say this, the largest swimming area is 50 meters by, and let me just draw a little visual here. So we're saying you want to make the best swimming area possible. You go 50 meters out into the lake. And then, of course, you can probably use just mental math here, how much width is left. Or if you needed to, you could just calculate what the width would have to be. It's 200 minus 2 times 50. But that gives you 100 meters. So it's 50 meters by 100 meters. So it turns out that if you want to maximize the area of a rectangle, where one side doesn't need any rope or fencing if it's a backyard, etc., you wind up making the length twice as much as the width. That's a property that grade 9, it's in the grade 9 curriculum. They're actually taught that. In grade 9, you guys would have just done it numerically, like I said. In grade 10, you guys would have used the fact that, hey, this is just a parabola. I think I can sketch it. Maybe I'll sketch it with a different color. In grade 10, you guys would have been, okay, this area is a function of L. It has x-intercepts at 0, 0, and 100. And it has a vertex at 50. And I found that vertex is 55,000. That's what grade 10 you would have done. But now we have our method using calculus where we set the derivative to 0 and then check endpoints, perhaps. One thing to say before wrapping up A, because this one was quadratic and opens down, you kind of know that when you find length equals 50, this corresponds to the vertex. We probably could have wrapped the problem up there, but I'm just establishing some patterns that we can use later. Anything you guys want to chat about? Maybe that question even seemed familiar to you. We should look at B. B says, due to the depth of the water, the area cannot extend more than 40 meters into the lake. So let's talk about how our this process would change. We've already done all the heavy lifting. But B is saying, green is a horrible choice. B is saying, okay, the domain of our area function is different in part B. The lowest the length can be in part B is 0. But now, due to our restrictions on the depth of the lake, we don't want people drowning. We can only go 40 meters out into the water. Guys, is our critical point that we found, that critical number, is that inside our new domain here, restricted domain? I see some head shaking. No, so in this case, the biggest possible area would just have to be at those endpoints. So you would say, okay, there's no critical points inside this domain. So I would really just have to check what's the area for the lowest value of L and what's the area for the highest value of L, which in this case is 40. And so obviously the biggest swimming area possible, we'll just go as deep as we can. And it would be 40 times 120. I think it would be 4,800 meters squared. How's the mental math there? 40, 40, 120. I think it's good. Of course, you guys will tell me if I make a mistake. So yeah, then that swimming area looks a little bit different. We can only go 40 meters out, and it's 120 meters wide. The area is a bit smaller, but so do you guys see how changing so real life can restrict the domain and range, might restrict the best possible area? Okay. So yeah, great little introductory question because you might have done it in grade 10. ties some things together from earlier grades, and then we introduced how to use calculus to solve an optimization problem. Let's continue to a question where we will need our calculus techniques. So here we have a cardboard box with a square base, and for whatever reason, we're packaging some product in here that has a volume of 8 liters. And maybe this product is like something edible or like a liquid, I don't know, so that we can make all kinds of different container sizes that will hold the 8 liters. Our idea is, because if we're making, let's say we're making tens of thousands, hundreds of thousands, millions of these packages, when you have to pay for the cardboard packaging and all that stuff, eventually that kind of adds up, and you want to create some packaging that minimizes the use of cardboard, but still fits in your product. So here we have a fixed volume of 8 liters, and we want to find the ideal possible packaging. Now, of course, everybody knows their metric conversions. 8 liters is 8,000 milliliters, and everybody knows how many centimeters cubed are in a milliliter. Do you guys know? 1 milliliter is exactly 1 centimeter cubed. So all you people that like doctor shows and stuff, when you see them say, give 100 cc's of this, that just means cubic centimeters. It just means milliliters. So this question is saying our cardboard box needs to hold 8,000 centimeters cubed for its volume. Okay, so let's apply the method we used before. We are minimizing the amount of cardboard to use. Now we're just going to keep things simple, we're just going to pretend there's no overlap. In reality there would be, but to keep things simple, we're just kind of going to minimize the surface area of this rectangular cardboard box. Now, when we get to these 3D measurement problems, you probably should just know how to develop an equation for surface area. For some shapes, you learn the formulas in grade 9. This one is just easy to reason out. We have a bottom of the box. We have a top of the box, and those are both x by x. So we have a top and bottom. So the area of the top and bottom will be 2x squared. And we can maybe you can add a note here if you want to for coming back to this later. Where'd that come from? It's the area of the top and bottom. And then we have 4 of these sides that are x by h. So this is an expression for the surface area of this square-based rectangular prism box. We run into the same problem as the previous one. We'd like to minimize this function, but it's a function of 2 variables. So just like the last one, we take our constraint and we use that to get this question in terms of 1 variable. I'm going to tuck that over to the side here. And just use my space well, make Ms. Plattner proud of me. So the constraint here is that the volume has to be 8,000 centimeters cubed. The volume of this box, it's a box, length times width times height, x times x times x. The volume of this box is x squared times h. This has to equal 8,000. And I would argue probably easier to isolate h. We don't introduce any weird roots or anything. So let's get h by itself. H is going to be the volume divided by x squared. So whatever that square base, those dimensions are, the height is 8,000 divided by that square base squared. So now we can get a surface area function just in terms of 1 variable x by replacing h with what h is equal to. So we have 2x squared plus 4 times x times 8,000 divided by x squared. Unlike the previous question, this isn't a parabola. You can't use your grade 10 techniques and find the vertex. We have to resort to calculus to do this kind of problem. Now, This one's actually not too bad to differentiate and solve. We're not going to find the derivative right now. We can do a bit of cleaning up first. So let's do that. The 2x squared term is fine, but 4 times 8,000 is 32,000. And x over x squared, we can write that as 32,000 divided by x. And I would even suggest, to make it easier to find the derivative, let's just write that as a power, 32,000 times x to the power of -1. That'll make finding the derivative a lot easier, in my opinion. Can we also talk about the domain of this surface area function? So I think everybody would agree that the lowest the lowest we can get for x would be 0. Like, you can't have a negative length for a box. That'd be kind of weird. But is there really any maximum value for x? As x gets really big, the height of the container would just shrink. In theory, you could have a box that is like a mile wide and a mile long, and the height would just be like a picometer or something like that, right? That'd be a silly box. But in theory, you can make x as big as you want. So we'll say the domain of this function, the lower value is 0, the upper value is infinity. So let's continue. So now we have a surface area function and we want to minimize it. So we go about our process, find the derivative, set it to 0, find those critical values, check our endpoints if necessary. So let's go ahead and do that, and let's find the derivative. I'll just say surface area prime of x. I guess I'm using black now. Yeah, this one's not too bad now that we wrote it like that. 4x and then minus 32,000. X to the power of -1 minus 1 is -2. And as we usually do, we are going to set that equal to 0. We have to solve this equation for x. Just using all the skills we've been developing in our high school math careers, this one's actually not too bad to solve for x. We can actually just get x by itself pretty directly. I'm going to rewrite that now as 32,000 over x squared. And if we just move one term to the right and just do some cross multiplication, we can actually get all the x's together. I'll show a few steps here. So we'll move that 32,000 over x squared term to the left. I got lots of room. We'll multiply up the x squared. Just multiply both sides by x squared. You get 4x cubed equals 32,000. And now we can just get x by itself using opposite operations. So x cubed is equal to 8,000. And so probably you haven't used your third root button in a while, but the third root of 8,000, I can show you what that is. You just have to ask. I believe it's exactly 20. I'll let you guys confirm or deny that. You know what? Where's my calculator? It's 20. It works out too nice to be wrong. Third root of 8,000. Of course it's 20. It's 20. You guys get 20? All right. Perfect. Now, let's have a little team talk here about, is it really necessary to check our endpoints? So if you think about a box that has a very, very teeny tiny value for x, its height is going to be incredibly massive, but its volume, if x is basically 0, its volume would just basically 0. Does that make sense to you guys? Be like an infinitely narrow box, really stupid. And then if x gets really big, you have a huge base, but a teeny tiny height, and the volume's basically 0. So checking the endpoints here, there's not really anything. If this was a test, I would say do not check endpoints because there's not a lot of value in it. But because we found the first derivative, the way we have it set up, the second derivative is actually pretty easy to find. We can actually tie in some talk about concavity. So the surface area's second derivative would be 4, and then bring down the -2. -2 times -32,000 is 64,000. And then take 1 off the exponent, -3. And we can write that as 4 plus 64,000 over x cubed. Now, if we think about the second derivative, x is always positive, right? This surface area function is always going to be greater than 0. 4 is always bigger than 0. X is always bigger than 0. 64,000 is always bigger than 0. Are you guys convinced it's always bigger than 0? What does that mean? It means it's concave up. So this function is always concave up, which means that point we found earlier, x equals 20, if this function's always concave up, that's a local minimum. We know that that's going to minimize our surface area. So I'm just going to add a little blurb about that. So x equals 20 centimeters gives the minimum surface area. We had a conversation about the endpoints. We just had a conversation with the concavity and showed it's a minimum. I'll tell you guys, in practice on a unit test, I would kind of give you some coaching. I might say, investigate the concavity of this function and show that it must be a local minimum. But checking the endpoints here would just be kind of weird. But yeah, there we go. So we're basically done. The x is 20. I might just go out over here where I have space. If x is 20, what is the height? The height we said was 8,000 divided by x squared. What's 8,000 divided by 20 squared? It is also 20. So what you guys have shown here is actually some like general principle that just applies all the time. If you want to minimize the surface area given a fixed volume, this also goes the other way. If you want to maximize volume given a fixed surface area, you should make a cube. A cube. I'll put that in big caps. A cube minimizes the surface area. And hence the cost of the packaging, etc., etc. Little therefore statement. Good stuff. So a similar type problem to the one we did before with the lifeguard and the ropes. But here we had to use our calculus techniques, but a very similar approach. You guys okay with what we did there? What you guys will need practice at, it's not so much the derivatives and the solving. I would argue nothing there was too crazy. It's the setting up of the equation that requires some practice. So I'm trying to give you guys some experience here in a few different areas. We're going to do one more today. Tomorrow we'll do a couple more. And then you guys just need to practice because I can't teach you every single possible type of optimization problem. That would take way too long. I thought this one is new for me to teach this year. I haven't done a problem like this in class before. So it's going to go fine. It's not going to backfire at all. It's going to work perfectly. But here's the idea. So Bort is playing with his dog on a beachfront. His dog is 20 meters down the beach. And what Bort is doing is Bort chucks a stick 10 meters out into the lake, perpendicularly into the lake. And this dog is going to go run and get this one. Hopefully that comes back in a second. Gets the stick. Come back, thank you. So let's do a little visual of our problem here. I won't make it too big. I don't want to mismanage my space and make Miss Plattner not proud of me. But here we have a beach. And I'll maybe just put a little B here for Bort and a little D here for dog. And then Bort throws his stick. I'll put an S out here. The stick is out into the water. He throws it 10 meters out into the water. And the dog really wants the stick. So the dog wants to get there as quick as possible. Now the dog can run along the beach, and I think this is for most people. This is true for anybody. Like most people can move along dry land faster than they can swim. So the idea is the dog can run along the beach. The dog could run all the way to Bort and then swim out and get the stick. Or the dog could maybe jump right in the water and swim directly there. Or the dog could run part way and then swim part way. Which one of those options is the fastest and minimizes the time to get to the dog? I suppose if I didn't want to be silly, I could have made this a lifeguarding question, because that would actually be a legitimate question. Where should a lifeguard dive in to save a swimmer and get there as quick as possible? But here we are. I already made the question. We're stuck using the dog. And I've already got my stock photo I stole off the internet, so we're just stuck using this one forever. All right, but how do we do this? We need to create an equation that minimizes the time it takes Bort to get to the dog. So the first thing we're going to do is we're just going to say, okay, well, we need to kind of establish a way of like measuring, okay, when is Bort's dog going to jump in the water? And we're going to say that we're going to let X be the distance from Bort where the dog jumps in. So if the dog, if X is equals to 20, then that just means the dog should swim right away. If we end up solving our problem and X is 0, that means that the dog should run all the way to Bort and then jump in. But we're kind of finding how far away should the dog be from Bort to jump into the water to minimize that time. What we also then have here is that the distance that the dog has to run before jumping in would therefore be 20 minus X, because remember the dog's 20 meters away down the beach. Are you guys okay with the setup so far? Okay, let's continue. The dog is going to swim from this point where they jump in to the stick, S, and we need an expression for that distance. That distance we can just use Pythagorean theorem. We have one leg, 10. We have the other leg, we called it X. And so this distance here, just using Pythagorean theorem, will just be the root of X squared plus 10 squared, which is 100. That just comes from Pythagorean theorem. So when you guys are going back and looking at this note, that came from Pythagorean theorem. We had that discussion in class. You could also rewatch this video. It's being posted. Those are all the distances in the problem. You guys okay with that setup so far? We're not trying to minimize distance. We're trying to minimize time. So you guys, we have to understand the relationship between speed, distance, and time. Perhaps you've seen the speed, distance, time triangle before. And I know some people are taking physics right now. But speed is distance over time. So if you write speed, distance, time in a little triangle, that helps you get an expression for the time. You just basically cover up the time. I'll shade it in here. To get time, time is distance divided by speed. So we now have kind of a way for us to find, to get an equation for the total time. So we'll start it off this way. You guys are my guinea pigs, so we'll see how this setup goes and see if I need to add more or take away more later. So the total time is the time running plus the time swimming. I don't know why I capitalized one and didn't the other, but we'll be consistent. Does that make sense, guys? The dog will run for a bit and then swim for a bit. So that's an expression for the total time. While using the speed, distance, time triangle, that would be the distance running divided by the speed running speed. I don't know. I'm not really worried about grammar right now. And the time swimming is the distance swimming divided by the speed swimming. And we have expressions for all of those things. We did that legwork in our diagram. We have the distance running. It's 20 minus X. We have the speed running. It's 5 meters per second. We have the distance swimming. It's that radical. And we have the speed swimming. So we now have an equation for the total time, the dog getting to the stick, in terms of one variable, the distance from Bort. And it's the distance running, which is 20 minus x, divided by the speed running, which is 5, plus the distance swimming. If you guys are okay with this, I'm just going to write it as a power just to get it ready to find the derivative. And we're all set up. The very last thing, because it's not so hard to do, there is a domain for x. X has to be between 0 and 20. I think it'd be kind of silly for the dog to run farther away from Bort to jump in the water. That obviously wouldn't minimize the swim time. So let's pause, digest. How was that set up? You guys, kind of reasonable? Follow along? Because now you guys can do the math. It's just find the derivative, set to 0, and solve. But it might have been a while. You might not have solved too many equations involving radicals in your last course. So I will do this one with you guys. How much space do I have? Let's zoom out here. Oh, Miss Plattner, maybe I should have done this stuff up here next time. It's okay. We got lots of space anyway. I might just have to go to different spots on my page. I might suggest, if you guys are okay with this, before we find some derivatives, let's just do 20 divided by 5. It's equal to 4. Minus 1 divided by 5 is 0.2. It's just, I think, getting rid of the fractions will make things easier, perhaps. And then let's say 0.5 times x squared plus 100 to the power of 1/2. Maybe that will just make finding the derivative a bit quicker. Maybe not, though. All right, let's find the derivative. Derivative of 4 is 0. The derivative of minus 0.2x is minus 0.2. Plus, okay. Oh, my Discord's popping off. My Potion Craft Discord I was talking about in the weekend. Okay, anyway. Hopefully no naughty words pop up. That would be very awkward. All right. Let's bring down the 1/2. Okay, you know what? I'm just going to mute. Apologies, YouTube. All right, we're just going to mute there. All right, bring down the 1/2 times 0.5. That would be 0.25. And then we have x squared plus 100. Take 1 off the exponent. That's negative 1/2. And multiply by the derivative of what's on the inside, which is 2x. That's our derivative. We're going to set that equal to 0 because that's what we do. Let's clean some things up. I'm just going to kind of shift things to the left a little bit on my page. Of course, you guys probably manage things a bit better than I did. So we have negative 0.2. 2 times 0.25 is 0.5. So we have 0.5x. And then that power of minus 1/2, I'm just going to write that on the bottom. And I'm actually going to make that as a square root. Plus 100. And this is all equal to 0. That's just me cleaning up the derivative and setting things to 0, writing things in terms of radicals so that I can solve this equation. You still might be wondering how on earth will we solve this equation. Well, I'll show you. Check this out. I'm just going to move the 0.2 to the right. That's all I'll do in this step. And what I'd really love to do, I'd love to isolate x. I'd love to get x by itself. The thing is, it's inside that pesky square root. So what we're going to do is we're going to square both sides. We're going to square everything on both sides. We're going to square the top of the left-hand side. That gives us 0.25 x squared. We're going to square the bottom. The square of root of x squared plus 100 is just x squared plus 100. And when you square 0.2, you get 0.4. And of course, what we did there is we square both sides. Square both. We're almost there. Now you can just multiply up the x squared plus 100. So we have 0.25 x squared equals 0.04 x squared, and then 0.04 times 100 is exactly 4, if I didn't mess anything up. Now that is something that you guys can collect like terms for and solve for x. We don't have to worry about the negative here because x is between 0 and 20. So me, because I mismanaged my space, I'll have to go all the way, I'm sorry, Ms. Plattner, all the way up here. I have to continue this. I can zoom out. And I'll finish things off up here. So bringing over the 0.04, so we get 0.21 x squared is equal to 4. And so x will be 4 divided by 0.21, and then we're going to square root that. The root of 4 divided by 0.21. And we're going to pray that this gives us a value between 0 and 20, because I've never done this question with the class before. Of course it's going to work. Nothing ever goes wrong the first time you do something. This is looking good. I got 19 point something, and when I root that, I get something nice and smack dab in the middle. I got about 4.36 meters. Did you guys get that as well? Perfect. Now, for the sake of time, no pun intended, this question asks for the minimum amount of time. Can we just wrap the problem and say, you know what, to minimize the time to get the stick, that's the spot where the dog should jump in. You guys okay with that? Just so you guys can get to practicing? Let's just wrap it up then. So the dog should jump in. The dog should enter the water .36 meters from boards. Of course, this isn't a general thing. This is based on how fast the dog can run. Now, when I made this problem up, I know dogs can run much faster than 5 meters per second, unless they're kind of old. But I just wanted to use values that gave nice decimals just to try this question out. But yeah, I think that went pretty well. Thanks for being my guinea pigs. So I borrowed from the text we use for practice, just kind of those concepts we use, a process you guys can use for solving optimization problems. I kind of have that here, but you know that it's usually equation, sometimes a constraint if your equation is in more than 2 variables, find the derivative set to 0 and solve using a lot of tools we already have. But yeah, I think we had to review a few solving equation techniques along the way. Anything at all you guys want to chat about? Okay, I'll pause, stop the recording then.